The ROV pilot almost didn't report it. It was 2007. A research vessel was drifting somewhere over the Gulf of Mexico, nearly a kilometre above the seafloor. The pilot had run hundreds of dives. He'd seen hydrothermal vents, deep-sea avalanches, and fish that looked like they'd been designed by something that hated beauty. But he had never seen this. On his monitor, at the edge of the camera's light, was a shoreline. Not metaphorically, not something that resembled a shoreline. One side, ordinary seawater, hazy with particles, moving the way deep water always moves, slowly, restlessly, alive. The other side, perfectly still, darker, glassy, as though someone had poured another ocean inside the ocean, and it had simply settled there, waiting. He moved the ROV closer. The boundary didn't blur. It didn't ripple. It held its edge like a knife cut. And then he saw what was floating along it. Fish, crabs, a shrimp suspended just below the surface of the dark water, not swimming, drifting, motionless. He pulled the ROV back, filed his report, and somewhere in the chain of people who read it, a marine biologist circled one line and wrote 3 words in the margin. Beneath the Gulf of Mexico, hidden nearly a kilometre below the surface, there are lakes. Not rock formations that look like lakes, not metaphors. Lakes, with shorelines, with waves, with a surface you can watch a ripple when the ROV gets too close. They are filled with water 3 to 8 times saltier than the ocean surrounding them. They have been sitting there, completely sealed from the world above, for thousands of years. And they are, by almost every measure, one of the deadliest environments on the surface of this planet. Scientists call them brine pools. Most things that enter them don't come back out. And yet, somehow, they are teeming with life. This is the story of the lakes that shouldn't exist. What formed them? What lives at their edges? And why the answer to that last question may be the most important discovery in the history of the search for life. Not just here, but everywhere. Knowing that brine pools are incredibly salty only answers part of the mystery. It doesn't explain where all that salt came from. To find the answer, we have to travel back nearly 200 million years, to a time when dinosaurs had only just begun to dominate the Earth. Back then, much of what is now the Gulf of Mexico wasn't a deep ocean at all. It was a shallow inland sea, connected only occasionally to the open ocean. As the climate became hotter and drier, enormous amounts of seawater repeatedly evaporated. The water disappeared, but the dissolved minerals remained behind. Layer after layer of salt accumulated on the sea floor, until some deposits became hundreds of meters thick. Over millions of years, these ancient salt beds were buried beneath newer layers of mud, sand, and rock, locking away one of the largest underground salt reserves on the planet. But the story didn't end there. Unlike most rocks, salt doesn't stay rigid forever. Over millions of years, the immense pressure from the sediments above caused it to behave almost like an extremely slow-moving fluid. It gradually pushed upward through cracks in the surrounding rock, forming massive underground structures known as salt domes. As these salt domes continued to rise, groundwater and seawater seeped into the buried salt, dissolving it and creating highly concentrated brine. Because this water contained far more dissolved salt than the surrounding ocean, it became much denser. Whenever the brine escaped through fractures in the seafloor, it flowed downhill into natural depressions instead of mixing with the seawater above. The boundary between the two is so sharp that scientists call it a halocline, a layer where salinity changes dramatically over just a few centimeters. Light bends differently as it passes through this boundary, creating shimmering distortions that make remotely operated vehicles appear to be looking across the surface of an ordinary lake. From above, it looks almost impossible. But these lakes obey the same laws of physics as everything else in the ocean. The real mystery isn't how they formed. It's why crossing that invisible shoreline can be so deadly. By now, we know these underwater lakes are unlike anything else in the ocean. But one mystery remains. Why do so many animals die after entering them? When remotely operated vehicles explored brine pools, they repeatedly captured the same unsettling scene. Fish, crabs, shrimp, and even octopuses lay motionless along the edges. Some appeared to have wandered into the brine by accident. Others looked almost perfectly preserved, transforming parts of the seafloor into what researchers described as an underwater graveyard. Imagine the ROV camera sweeping slowly across the seafloor. The light catches something. A crab on its side, claws still open. A fish suspended just below the surface of the dark water. Fins fanned out as though it had simply stopped. Perfectly intact, perfectly still. You are looking at an underwater graveyard. Every creature that drifted too close made the same mistake, and none of them made it back. Scientists nicknamed one site in the Gulf of Mexico the Jacuzzi of Despair. Animals could enter the pool with ease. The current carried them in, the density held them under, and the chemistry finished what the salt began. Most never made it back out. The ones that did barely escaped. The ones that didn't were preserved so perfectly that the seafloor around the pool looked less like a natural environment and more like a display case. The answer wasn't simply the salt. Inside the brine, oxygen is almost completely absent, while toxic chemicals such as hydrogen sulfide accumulate to concentrations that most marine animals cannot tolerate. Methane leaking from deep beneath the seafloor adds to this unusual chemistry, creating one of the most hostile environments in the ocean. For fish and other marine life, crossing the boundary is often a one-way journey. Yet, despite these lethal conditions, scientists found thriving communities living just centimeters away from the brine. Somehow, life had adapted to one of the deadliest environments on Earth. The answer wasn't another predator or a hidden escape route. It was something far smaller than anyone expected. Instead of an empty wasteland, scientists found one of the richest ecosystems in the deep ocean. Vast colonies of mussels covered the seafloor. Giant tube worms stretched up from the sediment, while shrimp and crabs patrolled the edge of the brine, surviving only a few centimeters from water that could kill most marine animals. It seemed impossible. Almost every ecosystem on Earth depends on a single source of energy, the sun. From forests to coral reefs, life is ultimately powered by sunlight. Remove it, and sooner or later, the entire food web begins to collapse. But sunlight has never reached the bottom of the Gulf of Mexico. So where was all this life getting its energy? The answer is chemosynthesis. Instead of capturing energy from sunlight through photosynthesis, certain bacteria and archaea obtain energy directly from chemical reactions involving methane and hydrogen sulfide rising from beneath the seafloor. They use that energy to produce organic matter, creating the foundation of an ecosystem that exists entirely without sunlight. Many of the mussels living around brine pools survive because billions of these microbes live inside their gills. The bacteria convert chemical compounds into nutrients, while the mussels provide them with a safe place to live. It is a partnership so successful that neither organism could survive in this environment without the other. Giant tube worms have taken that partnership even further. Adult tube worms have no mouth, no stomach, and no digestive system. Instead, they house dense colonies of chemosynthetic bacteria inside a specialized organ called the trophosome. The bacteria produce every nutrient the worms need, turning toxic chemicals into the fuel that keeps the entire animal alive. Scientists have found similar chemosynthetic ecosystems around hydrothermal vents and cold seeps, proving that sunlight is not the only foundation on which complex life can be built. Brine pools changed one of biology's oldest assumptions. Life doesn't always need sunlight. Sometimes, chemistry is enough. And once scientists accepted that idea, an extraordinary possibility emerged. If chemistry can sustain life without sunlight today, could it have done the same billions of years ago, when life first appeared on Earth? That question has fascinated scientists for generations. Every living organism, from the smallest bacterium to the largest whale, can trace its ancestry back to a time when chemistry somehow became biology. Exactly where that transformation happened remains one of science's greatest mysteries. Brine pools don't provide the answer, but they may preserve some of the closest modern examples of the kinds of environments in which early life could have survived. The microbes living around these underwater lakes survive using methane, hydrogen sulfide, and other chemical compounds, relying on metabolic pathways that many researchers believe are among the oldest on Earth. Instead of showing scientists how life began, they demonstrate how life can persist under conditions that resemble parts of the ancient planet. Among the organisms attracting the most attention are archaea. Although they resemble bacteria under a microscope, genetically they are very different. Many scientists consider them among the closest living relatives of Earth's earliest life forms. They can survive crushing pressure, extreme salinity, toxic chemicals, and complete darkness, conditions that would kill most complex organisms. Modern DNA sequencing has revealed that many microorganisms living around brine pools possess genes unlike those found anywhere else on Earth. Some have evolved unique ways to tolerate salt, repair damaged proteins, and generate energy in environments once thought uninhabitable. Every new genome gives scientists another clue about how life adapts, evolves, and survives under extreme conditions. The deeper researchers look into these extraordinary microbes, the more they realize they are doing more than studying Earth's distant past. They are building a blueprint for where life might exist beyond our planet. Scientists no longer see brine pools as strange underwater lakes. They see them as natural laboratories for astrobiology, the study of how life might exist beyond Earth. Here is the connection. If microorganisms can survive in complete darkness using nothing but chemical energy, no sunlight, no photosynthesis, no surface world at all, then the same chemistry could be running right now on worlds that have never seen a single ray of light. Two of the most promising candidates lie hundreds of millions of kilometers from Earth. Jupiter's moon, Europa, is believed to hide a global ocean beneath an ice shell that may contain more water than all of Earth's oceans combined. Saturn's moon, Enceladus, appears just as remarkable. During its mission, the Cassini spacecraft flew through enormous plumes erupting from the moon's south pole and detected water vapor, salts, methane, hydrogen, and organic molecules. Together, those ingredients suggest that a potentially habitable ocean exists beneath the ice. No one knows whether life exists there, but scientists now know that the absence of sunlight is no longer enough to rule it out. That realization has transformed Earth's most extreme environments into testing grounds for future space exploration. Brine pools, hydrothermal vents, and subglacial lakes are known as planetary analogues because they allow researchers to study how life behaves under conditions that may resemble other worlds. NASA's Europa Clipper is equipped with instruments designed to study Europa's chemistry and search for potential biosignatures, chemical patterns that could indicate past or present life. While the spacecraft will not drill through Europa's ice, the data it collects will help scientists determine whether the moon has the conditions needed to support biology. It is a remarkable thought. The search for alien life may not begin with a discovery on another planet. It may begin with the strange microorganisms that have been quietly living beneath Earth's oceans all along. The search for alien life may one day lead us to distant worlds, but some of its most important clues are still waiting here on Earth. Scientists still don't know how many brine pools exist beneath the world's oceans. Every deep-sea expedition continues to uncover new surprises. In 2022, researchers exploring the Gulf of Aqaba discovered an entirely new system of brine pools, more than 1,700 meters below the surface. Their undisturbed sediments preserve a remarkable record of ancient earthquakes, tsunamis, and climate change, making them one of the most valuable geological archives ever found beneath the sea. And these lakes continue to reveal something else. Every expedition uncovers microorganisms, unlike anything scientists have seen before, reminding us that much of Earth's microbial diversity is still completely unknown. Each discovery expands our understanding of how life adapts, survives, and evolves under conditions once thought impossible. Perhaps that is the greatest lesson brine pools have to offer. For centuries, exploration meant crossing oceans, climbing mountains, and reaching distant planets. Today, some of the greatest discoveries are being made in a place we have barely explored at all. We have sent spacecraft beyond the solar system and landed robots on Mars. Yet vast areas of Earth's deep ocean remain unmapped, unseen, and unexplored. Brine pools are only one chapter of that hidden world. A lake that should never have existed became a window into Earth's ancient past, a guide in the search for life beyond our planet, and a reminder that the greatest mysteries are not always the ones waiting among the stars. Sometimes they are waiting in the darkness beneath our own oceans.